Hello everyone. Today we'll learn about SPICE. It is in chapter 4 under combinational logic circuit. So what is SPICE? Well, SPICE is actually a simulation program with integrated circuit emphasis. This is the full name for SPICE. Okay. It is a program that simulates electronic circuits on computer by viewing any voltage or current waveform in the circuit. Okay. Originally, it is developed in 1970s at University of California, Berkeley. It is released in 1972, which is called the SPICE-1. Well, actually, it is based from cancer computer analysis of nonlinear circuits excluding radiation. It used device model and circuit netlist to predict circuit behavior, voltages, and current. Okay. So SPICE can calculate voltages, currents versus time. This is called the transient analysis. Or it is a voltage and current versus frequency. It is called the AC analysis. Also, it can predict performance and power consumption of the circuit. Other than these two analyses, you can also do the DC analysis. Okay, for DC analysis, you will calculate all the important points, meaning that for all the transistors in your circuit, you will check whether the transistor will be in the saturation region and so on. Okay. Today, SPICE is available from many vendors. Some are using schematic drawing to help you to draw the circuits to be simulated. Okay. Originally, you have to include all the circuits information through the netlist, but now it is no longer. You just use a schematic editor. Okay, and there is several versions of a commercial SPICE which is available today. For example, HS SPICE, IS SPICE, T SPICE, and so on. Okay. This is some example of CAD example. The first one is from the, if you go to the site, there is several tools over here. Okay, there is OCAD by the OCAD, PSpice student version, okay, LT SPICE, Dot SPICE, and so on. Some are free actually. Okay, so what is SPICE? As I said just now, it is used to simulate the circuit. So this is the simulation. This is an example for Synopsys H-SPICE. Synopsys use H-SPICE. Okay. If it is from Tenet, it will be T-SPICE over here. Okay. So if you have drawn your circuit and you want to make sure to check whether the circuit function as it should be, you simulate the circuit using the H-SPICE engine. Okay. And similarly, at the back end, if you draw your layout, after you have done the DRC, you do LVS, meaning that the layout is equivalent to your schematic device. Then you do the PEX, which is a parasitic extraction. And from there, you include all the parasitic values and you simulate again your circuit. Okay, so the simulation will use the H-SPICE engine. So this is another whereby this where the circuit simulation will be done. When you simulate your circuit, okay, actually the simulation is done based on the netlist. This is the schematic entry. You draw your circuit. The circuit will be converted into netlist. This netlist is being simulated by the appropriate SPICE engine. Okay, it depends on the technology file over here. Might be it is 290 nano, 90 nano, and so on. And after the simulation is done, you have two outputs. One in terms of waveforms, whereby you can see all the relationships between the voltages or might be current and so on. And another one is the output in a text file. This is the some sort of the netlist plus all the waveform and all the information regarding your circuit. Okay, so in SPICE element, when we draw our circuit, we have so many devices. We have resistor, capacitor, diode, and so on. So each of these elements will be indicated by the first letter. For example, resistor, the first letter will be R, inductor L, sub-circuit will be X, and so on. Okay, I'll show about this later. And the units used in the simulation, for example, if you want to write 90 nanometer, it will be 90N, right here, N. It represents 10 to the minus 9, which is nano. For example, you have a resistor of 100 kilo ohm, so you write 100K. K represent 10 to the power of 3, which is kilo. This is for the capacitor, example of capacitor, 100 F. The small f is the femto, and the capital F is the farad. Okay. So, in this for each of the semiconductor devices, okay, we have a model statement. Dot model right here. Okay, we have element, which is our devices, and how to represent this element. So we need a model statement. For example, this is for the MOSFET, M, the first letter, M, name, might be M, PMOS, M, NMOS, and it is located between drain, gate, source, body. Body is your part and type, whether it is NMOS or PMOS. Okay, and this plus you have W, which is equal to width, L equal to length, and so on. This is the model for that particular MOSFET. Different engine will have a different model. Okay, so in general, the model statement will be dot model, mod name, type. This is all the parameter just now, W, L, and so on. Okay, and then this mod name is the name of the model for the device. Type refer to the device and can be of anything. You have several devices, right, just now. Okay, so it is actually just a model to represent the MOSFET. For example, we have a beautiful lady like here. This is the Cindy Crawford. So, device also needs a model. Okay, so this is the SPICE modeling. M stand for M MOSFET 1, meaning that it is transistor number 1 between drain, gate, source, body, and mode. Okay, length is 1 micro, width is 10 micro. Okay, see, model name, parameters. Okay, so in the netlist, you'll see this dot model and mod, the model name. This is type and MOS, and this is all the parameters that represent your model. Okay. So for model, for transistor models, okay, there are so many models to be used actually. Okay, even though it is a simple devices, it has a very complicated behavior, meaning that you have to represent your transistor in the saturation region, in the triode region, and so on. That is for the MOSFET. For BJT, you have to do the modeling in the active region, saturation region, and cutoff. So that's why there exists a variety of different models that range in complexity to describe the behavior of your transistor. So this is one example of model NMOS. So if you see over here, the parameters, they have so many parameters that describe the behavior of the transistor. They include all the value for the parasitic capacitance between gate to drain, gate to source, and so on. Junction capacitance. Similarly, for the PMOS, just now is the NMOS. For the PMOS also, you have several parameters that represent the behavior of the transistor. And this is at level 3. I will show later. There is so many levels in describing the behavior of the transistor. And in the netlist, if you see the plus sign over here, this sign meaning that it is a new line, but it is extension of the previous model statement. Okay, so this is another example taken from another model. Okay, so still level 3, but if you see over here, the parameters over here, it is more than the one that I have shown in the previous slide. Okay, so what are those parameters? This is all these parameters. So if you see over here, VTHO is the threshold voltage, ideal threshold voltage, for example, DVTO for coefficient of short channel effect, and so on. There's so many parameters. Okay, CJ, just now I mentioned about the junction capacitance between, so this is source drain side junction capacitance, CJSW, CJSO between gate source overlap capacitance, and so on. This is for the process related parameter. The gate outside thickness, what is the thickness of your gate outside, gamma for the effect near interface, doping depth, and so on. Okay, another temperature modeling parameter, meaning that you will describe the behavior of the transistor if you vary the temperature. Okay, XTI junction current temperature, TCJ temperature coefficient for CJ. Okay, and just now I mentioned about the level. Okay, if you see the first or the earlier model used just a level 1, which is the simplest, meaning that all the parameters describing the behavior of transistor is just enough to model the transistor and you'll get the simulation result. It doesn't cover all the parameters that I have mentioned just now. And then it move to level 2, level 3, and so on. Okay, and then we have a BC model, which is level 13 in HSPICE. Okay, so example, this is level 28 PSIM derivative, 31, this is the level used by Motorola, 36 by Sharp, and so on. Okay, 47, 49 PSIM 3, both PSIM 3, but 47 in version 2 and PSIM 3 is for version 3. Okay, so all these are the transistor models for IC design. Okay, this is the complete level, I think, from level 1 until 50 something. This is taken from the Synopsys HSPICE. So if you see, up until 58. Okay, so what is BSIM? BSIM is Berkeley short channel IGFET model. IGFET is insulated gate field effect transistor. Okay, it is starting at Berkeley. Okay, it refers to family of MOSFET transistor model for integrated design. Okay, and we have a compact model coalition council or coalition CMC that adopt BSIM as a standard model. Okay, so since 1990 up until now, there is several BSIM, which is the level just now. Now we have a silicon on insulator. Okay, we have a multi-gate MOSFET. It will use different type of BSIM. Okay, so this BSIM model features all the distinct vertical, carrier drain induced, depletion charge, channel length, and so on. Basically, for simulation that we will use in Synopsys, it will be BSIM 3. Okay, this is there is several versions actually for the BSIM 3, and see, this is all the parameters that describe the behavior of the transistor in BSIM 3 model. Okay, now we have BSIM 4, which is the extension of BSIM 3. This is for the deep submicron. Okay, so this is the current. If you see, the BSIM 4 will check the gate tunnel current and so on. Now we have BSIM 6. This is for bulk MOSFET model. Okay, so this is the evolution from the bigger transistor until now it is about 14 nanometer.